All right, welcome everybody. This is our first talk of the winter speaker series for the Western U.S. Paleoglaciers Working Group, and we're excited to kick off the series with Dr. Bethan Davies. Quick introduction for Dr. Davies. She undertook her PhD research at Durham University, followed by postdoctoral research at the British Antarctic Survey, Aberystwyth University, and a lectureship at Royal Holloway University in London. She is now a professor of glaciology at Newcastle University. Her research quantifies how ice masses behave in different climates and environments and has a global geographical coverage, including the British-Irish ice sheet, Patagonia, the Andes, Alaska, Austria, Svalbard, and the Antarctic Peninsula. She has undertaken multiple remote polar expeditions to the Antarctic, the high Andes, and the Arctic. She was awarded the Richardson Medal by the International Glaciological Society last year in 2024, the Medal for Antarctic Education and Communication by SCAR in 2022, the Gordon Warwick Medal for Excellence in Geomorphological Research by the British Society for Geomorphology in 2021, and the Lewis Penny Medal by the Quaternary Research Association in 2014. She is a member of the Board of Directors and trustee of the charity Antarctic Science Limited, a member of the UK Antarctic Place Names Committee, chair of the UK Arctic-Antarctic Partnership, and co-chair of Diversity in Polar Science Initiative. She is currently editor for Quaternary Science Reviews and somehow has time to speak to us on this Friday afternoon from Newcastle. So thank you again, and please take it away.
Yeah, well, thank you so much for the invitation to talk to you, and I'm really pleased to be talking about some research I've been doing across the Americas. It's really going to be kind of two separate projects, one on Alaskan glaciers and then one on the Andean glaciers. And what I thought was interesting when I was doing these two separate projects was how we're seeing quite a coherent signal in all of these places. The reason I think for this group we all understand the reason why we want to do this research, but all of these glaciers are threatened by rising temperatures. So this figure by a well-known paper by David Rounce et al. Shows the sea level contributions by 2100 for different regions of the world, and the colours in the little circles are for different temperatures. So 1.5 degrees centigrade above pre-industrial is blue, and then 4 is red. And under all of these scenarios, Alaska is likely to be one of the biggest contributors to global sea level rise. And the glaciers in Alaska have an important cultural significance, but they're also one of the most significant drivers of sea level rise from glaciers. And in comparison, across the Andes, these very small glaciers are significantly threatened by glacier recession, in the tropics, may even disappear by 2100 under the warmest scenarios. So all of these show the observations we have on a global scale by papers, by teams such as the Huguenot paper, show an acceleration of glacier recession over the last 21 years, and we'll expect to see this continuing. When we look at the state-of-the-art projections from global scale glacier models, they all show a very strong dependence on temperature. So we have a glacier MIP comparison by Ben Marzian et al., and then we have the Rounce et al., OGGM and PyGEM comparison. All of these for both the Southern Andes and Alaska show quite a linear projection for the future. So these models, whilst they are state-of-the-art and extremely useful for predicting future glacier behaviour, are quite simple, and they omit some key factors in controlling glacier mass balance. They don't necessarily capture the threshold response of glacier change. And if we want to improve projections, there are some things that we might want to consider. The first is that if we look at temperature change from now to 2100, it's of a fairly similar order of magnitude to what we've seen from the pre-industrial to the industrial era. So we're about 1.3 degrees centigrade of warming in 2023, and we're currently looking at about 2.7 degrees of warming by 2100. So a similar time range and a similar temperature range from now to 2100 as from the pre-industrial era to the present day. So that's quite important for understanding some of the ways in which glaciers have responded to climate change in the past and help us capture how they might behave in the future. We also know that these longer term glacier reconstructions that predate the year 2000 can help us understand some of the important processes and feedbacks that we need to capture in regional scale glacier mass balance modelling in order to make more effective projections. And they can also be more effective if we're modelling over a longer time frame, because these glaciers and these reconstructions can provide calibration data, ensuring that lags such as response times and ice temperature variations are properly accounted for. And it was noted in the last IPCC report that there's a lack of these longer term reconstructions, and that this inhibits our ability to quantify the trends and to calibrate and evaluate models to simulate past and present future glacier behaviour. So it's against that backdrop that I decided to start looking at the glaciers of Juneau Icefield in Alaska. So it's partly in Alaska, partly in British Columbia. And if we go here, you can see the national boundary goes straight through the dividing line. But as glaciologists, we're fully within the Alaska Region 1 of the Randolph Glacier Inventory. So if I inadvertently call it Alaska rather than Alaska and Canada, that's probably why. And I wanted to create a long multi-temporal analysis of the glacier behaviour in this region. So the first thing I wanted to do was constrain the geomorphology of the ice field. So we undertook geomorphological mapping, ice field wide, using Sentinel imagery. There is higher resolution imagery available, but I think at the scale we were working, Sentinel was very appropriate. And then I also went into the field and ground truthed this in 2022. And if there are any cosmogenic nuclide enthusiasts in the group, which I think there are, we collected a lot of cosmogenic nuclide samples during that field season as well. And they're currently in analysis, and hopefully we'll have the results quite soon to help us look at the even longer time scale of glacier behaviour. And we also did a lot of data mining, because there's a lot of naval surveys and other bits and pieces of information that could help me to pin down the ice field in time and also look at glacier extent. Now there's a long time gap between this near glacial maximum, which has a very distinctive geomorphological footprint, and the start of the satellite era. But that is not a problem in Alaska, because there are some amazing aerial flight surveys that were flown in both 1948 and again in 1979. And these aerial surveys covered, the first one covered the Alaska component, and the second one in 1979 covered some of Alaska and also some of British Columbia and Canada. So this enabled us to have these aerial photographs over the whole of the ice field, and these are now freely available through the USGS. The problem with these images is that they don't have any geospatial data associated with them, so they're quite difficult to use in a GIS. And one of the things that we did in this program was we used MicMac to produce new orthomosaics and digital elevation models across the whole of the ice field in 1948 and again in 1979. So it's a bit like doing the world's hardest jigsaw puzzle and building an algorithm to do it for you. This required quite a lot of human oversight, because there's often images that are a bit torn or have a big thumbprint on or a bit of sellotape on or something like that. But we also used automated new algorithms that we developed specifically in MicMac to develop these new orthomosaics. Those algorithms are all open source. The code is freely available online, so you can find more aerial photographs and you can make your own digital orthomosaics and digital elevation models, should you wish. So this gave us the icefield extent in 1948, again in 1979, and that then brings us up into the satellite era. So we then were able to create elevation change and area change from the Little Ice Age, and then the mid-20th century, and then in the late 20th century. So we had a really long multi-temporal record that was And the value of it is integrating these archival data sets and geomorphological mapping with remotely sensed data to give a very temporally rich record of glacier change. So what did we find? Well, this map shows all of the glacier area change. So we have dark red is the glacier extent in the Little Ice Age, and then the white is glacier extent in the year 2019. And then the yellow and the orange on the ice field is the flat plateau of Juneau ice field. So where it's all yellow and orange, the ice surface slope is very low, kind of under 3 or 4 degrees surface slope. And if we look in a little bit more detail, we can see that all of the glaciers have shrunk substantially, which is what we'd expect. It's a common theme that we'd see in many parts of the world. So all of these glaciers have shrunk. There's some dashed lines there for Mendenhall Glacier, which are the naval surveys. And if we look at the overall rates of change in kilometers squared per annum, we can see a really substantial acceleration in that rate of change. So from 1770 to 1948, the ice field overall shrank at just 3.7 kilometers squared per annum. And then from 2015 to 2019, it was shrinking at 45 kilometers squared per annum. So it's shrinking substantially faster now than it was even 20 or 30 years ago. We're also able to look at volume loss. So these images here, they show the ice field thinning from 2000 to 2010 and 2010 to 2020. And where it's dark red, it's thinned more. Where it's light red, it's thinned less. And the graphs, the top graph shows the change in area from 1650 to 2020. And then we've got DHDT. This is the mean glacier area averaged thinning rate for different types of glaciers around the ice field. And then the bottom graph shows the change in volume in kilometers cubed per annum. So the dashed lines in that bottom graph, therefore, if we assume an earlier timing for Little Ice Age or a later timing for Little Ice Age, respectively, I assumed an age of 1770 for the Little Ice Age based on the literature that people have published. And they show a really substantial acceleration in all of these different factors after about 2005. So from 2005, the rate of change has accelerated, and the ice field is now losing a substantial amount of glacier ice every single year. So in fact, the area change is 5 times faster than it was in the late 20th century, and the ice volume loss has doubled from 2010 to 2020 compared with 1979 to 2010. So we're now losing 5.4 gigatons of ice every single year. And just to remind everyone just how much ice that is, that's a single gigaton of ice over Manhattan. So it's losing 5 of them every single year. So what's causing these changes? What's driving these changes? Well, we dug down into the various information that we could find. Juneau Icefield's a very special ice field, and one of the reasons why it's so special is because there's an extremely long and detailed mass balance record produced by the excellent Juneau Icefield Research Programme. So we have 2 independent mass balance records from Taku Glacier and Lemon Creek Glacier, and I've plotted them on here. And these 2 dashed lines are the height of the plateau. So the plateau is lower at 1,200 meters in the southern part of the ice field and reaches about 1,500 meters in the northern central part of the ice field. And what we can see is that after about 2005, that ELA for these glaciers is quite frequently crossing onto the plateau and reaching the height of the plateau. I also looked at snowline altitudes. I mapped these manually for about 5 years from 2019 to 2023. So in the map here, the black lines are the snow lines on the ice field. And the chart down here with the box plots is the elevation of the mapped ice fields. All the ice fields I can find at the end of the summer, all across the ice field. And the bar there is the mean elevation of the ice field. And what we can see is that increasingly frequently, the ice field end of summer snow line is intersecting with the plateau and occurring right on the plateau. And then the final piece of the jigsaw is this last graph here with all these coloured dots in the bottom, and that is the ice field albedo. So using a single satellite sensor, and these are the different albedos for the summative albedo for the whole ice field for the different months. And that summer albedo, there's a statistically significant decrease over time. So as these end of summer snow lines are intersecting with the plateau, the ice field as a whole is darkening. So the ice field is absorbing more solar radiation and accelerating melt. And crucially, that melt is now happening on the plateau, across the whole of the plateau. So we're seeing thinning across the whole of the plateau, loss of snow across the whole of the plateau, and increasing darkening of the ice field. And alongside these processes, we're also witnessing an increase in fragmentation of the ice field. And one thing that I observed when I mapped the entire ice field was that there are a number of glaciers that had become disconnected or separated with bare rock in the middle of them. And every time I observed this within a flow unit, I mapped it. And because I have the imagery, I can put a timestamp on each of these disconnections through time. So you can see an increase in the number of disconnections observed in each time slice. This photograph shows a nice example. So if you look in the bottom right of the photograph, you'll see that there's glacier ice in this valley, a bit of avalanching snow on the valley side. But that glacier flow that used to flow into this valley is now no longer flowing. What we have now here is a dark band of rock that entirely separates the glacier accumulation area with the glacier tongue. This bottom graph shows the elevation of these disconnections. So it's the elevation with the standard deviation, the black dashed lines, the height of the plateau, and then once again we have the ELAs. So these disconnections are happening at a fairly consistent altitude. They're happening where the ice is thin, where it's steep, where it's heavily crevassed. And what's happening is that these ice falls encircle the ice field. All around the edge of that flat plateau, we have ice falls. And as the snow line is rising, we're getting increased melt in these ice falls around the edge of the plateau. So as we raise the ELA, as we raise the snow line, we get increased melt in these points of vulnerability on the glacier, where the ice is thin, heavily crevassed, and very steep. And that means that the ice is vulnerable to these disconnections and bare rock appearing within the glacier ice. We then see a statistically significant acceleration and thinning for the glacier tongues that have been disconnected from the glacier ice above. They start to stagnate and they start to thin very, very rapidly. What I think we're seeing is we're dangerously close to the point of no return. As we're getting an increased temperature and decreased solid precipitation across the ice field, the ELA is increasingly appearing on the plateau. So we're not only having a vastly decreased area accumulation ratio, but there's also a change in albedo, which is increasing the melt in the surface mass balance feedback. But there is also now thinning on that plateau. And that's dangerous because as we thin into warmer air. And so we have our thinning and surface mass balance elevation feedback. And then because we have these ice falls around the plateau, as the ELA crosses these ice falls, we're getting increased fragmentation of the ice field, getting increased bare rock, which decreases the albedo, and we're getting decreased ice flow, which increases debris cover. All of these things contribute to more fragmentation. What this means is that we have a number of melt accelerating feedbacks that are operating on the ice field. And these can mean that it's a hysteresis that is essentially irreversible on meaningful human timescales. I think we're very close to a fairly permanent loss of this ice field if these processes are allowed to continue to accelerate and to continue. What's particularly concerning is that this isn't the only plateau ice field in Patagonia. This is a photograph of us having gone to sample that nunatak in the background for cosmogenic nuclide samples. And you can see just how flat this ice field is. But all of these ice fields are likely to be vulnerable, not only in Patagonia, but in other parts of the world where we're seeing similar processes of rising snow lines to a difficulty, a hysteresis in the system. And that's because even if temperatures stabilize, if the ice field has thinned to the point that it's got a lower elevation, it will be in warmer air and will continue to thin. So none of that was particularly good news. I think we're not yet crossed the threshold. I think we can still save these ice fields, but we do need to take meaningful action to reduce surface melt and surface the continued rise of the snow lines across the ice field. So we thought, well, I wonder if this is happening in South America. And rather than just doing one ice field, we thought, right, we'll do the whole of South America. That will be fine. And we wrote a new project to do this, which is called Deplete and Retreat. It's a big project. We've got many, many partners and project team members. And our goal was to try and reconstruct ice area and elevation change over a 200-year timescale across the whole of South America. So this project is still in progress, but I'm really pleased to have some really early initial results to show you. And one of the first is that we have already mapped the late Holocene moraines across the entire spread of the Andes. These photographs show some of the wonderful diversity in the geomorphological imprint of this neoglacial maximum across the Andes. Probably the Little Ice Age is probably not an appropriate term to use in southern Patagonia, so I prefer to call it something like the late Holocene neoglaciation. But in all of these sectors, we see an acceleration in loss. So here we have glacier rates of change from the Little Ice Age to the present day, or the late Holocene to the present day. The circles represent our area extents, and then we've got the published records of glacier change. And what we can see is there's still quite a big time gap in between these observations. And it makes it difficult for us to understand the trend properly, and it makes it difficult for us to understand the timing of acceleration and exactly what processes are operating. So the timing of this acceleration is still challenging to untangle. So what we have been doing is using some really beautiful declassified spy satellite imagery. And this is really cool kind of James Bond style operation, because what happens is with these low elevation satellites is that they would take images on their cameras, and then when the film is full, it just parachutes out of the aeroplane and gets caught in midair by another aeroplane, which I think is really, really clever and really, really cool. So here are the Corona and Hexagon satellites that give us really beautiful imagery from the 1960s, 70s, and 80s. And you can see these re-entry modules coming back to Earth. And these are widespread across the Andes. And so we've been collecting this data, and we have been trying to make new orthomosaics and new digital elevation models using a mixture of these declassified spy satellite imagery, and also aerial photographs and any other data that we can find. So this is work in progress being led by Owen King as part of Deplete and Retreat. And just like in Juno, it's involved us having to generate new algorithms. So we have a new branch of MICMAC called Spy MICMAC. And when these are published, all of those algorithms will be made available for people to produce their own imagery, as well as all of the orthomosaics and DMs will also be made available, as they are for Juno Icefield. So this will enable us to calculate rates of change in that crucial mid-20th century period between the Little Ice Age and the year 2000, when we start to get really good records of glacier change, and help us to look at the area change, but also the rate of volume change across the Andes. So overall, America's wide, from Alaska to Peru to Bolivia to Chile, we've seen an acceleration in glacier mass loss. And I think what we've found from this longer term perspective is the role that thresholds and melt accelerating feedbacks have in accelerating this loss. I think it's important to highlight how future change risks passing some of these tipping points, which could make the glacier loss effectively irreversible on human timescales. And our intention, particularly for America, for the South America as part of depleting retreat, is to use explicitly these paleoglacier reconstructions to improve calibrations for numerical models to make more skillful future simulations. So, and with that, I can finish and take happily any questions.
All right. Well, thank you so much, Dr. Davies, for that excellent presentation. Very, very interesting findings, and I'm sure we have lots of thoughts running around people's minds right now after seeing that take-home message, and I'm sure some questions too. So, folks on Zoom, if you just want to raise your hand, we can start a queue of questions. Go ahead, Jason.
Thank you. Really impressive work. It's really great to see you give the talk of the paper that we know about from the Juneau ice field. It's just fantastic. I wanted to know if, given that ice cap is near the town of Juneau and the JERP program has been running for so long, I wanted to know if there are any weather station data spanning some decades back in time that might give you a sense of what kind of temperature variability has been recorded locally, or maybe even precipitation. Like, what are the climate data look like through the last century?
Yeah, there's a weather station in Juneau. So there's quite a detailed weather station near Juneau Airport, and we use that in the paper. So in the full, I think it's in the supplementary data of the paper, there's quite a long temperature record. And then I also compare, when I look at the glacier behavior over the longer time scale, there's a temperature record reconstructed from a lake further north in Alaska. So over that longer time period, we've got the glacier lake temperature record. And we also have ERA5 reanalysis. So we use that as well to look at the system change, because there's a change in precipitation patterns after 1976, and that explains some of the change in behavior. But it doesn't explain the change in behavior after 2005, when we're seeing an increase in precipitation, an increase in temperature. The precipitation records from Juneau tell us that there's a decrease in solid precipitation due to a shortening of the winter accumulation season. So the summer season's becoming a bit longer, and some of the things that used to fall as snowfall on the shoulders of the season are now falling as rain. So there's quite a lot of detailed climate data in that information. What we've also done is there's another paper which has just been published. That's been published in Journal of Glaciology, where we've used COSIPY to model the surface mass balance of Juneau icefield. And that's taken in directly some of that climate meteorological data and applied it to surface mass balance modeling across the whole of the icefield. We tried to model the icefield with a more simple mass balance model, and it was too complicated, too much topographic variability. But COSIPY provided some really great insights into the mass balance behavior of the icefield using those data observations.
Dick, go ahead.
Thanks. Yeah, really a great talk. You mentioned that that you chose 1770 as the peak of the Little Ice Age, but that there were other options, and I was just wondering if you could walk us through your thought process for choosing that as the peak, and what else were you considering choosing, and what are some good references that you'd sort of let me know about to if I need to go down that path.
Yeah, so the timing of that late Holocene neoglaciation is quite variable depending on where you are. In Juneau Icefield, there is a pretty clear sea level record of glacier isostatic adjustment, and there's also some good dendrochronology records. There's also a little bit of radiocarbon dating. So for Juneau in particular, reviewed all of that data, and there was a consensus among multiple papers from different author teams using different techniques of 1770. But in other parts of Alaska, people have made cases for an earlier or a later Little Ice Age. So that's why I also calculated rates of change from 1650 and 1800 just to capture some of the uncertainty. All of that, if you look at the supplementary information for the paper, there's a whole couple of pages on the glacial geology and the timing of the Little Ice Age. For the work across the Andes, because the timing of that late Holocene near-glaciation is quite variable, we used whatever data we could find, whatever chronological data we could find. So there's a geochronological database associated with the paper with all the published relevant chronological information we can find. So there's a few cosmogenic nuclide ages, there's a few dendrochronological ages. For Patagonia, we have the PatIce database already, so we could use that. But there's also in Peru and Bolivia, the timings are quite different. And we also did some original lichenometric dating, which we did quite quickly whilst we were in the field when we were up in Chile, when we were up in Peru putting up a weather station. So I think look in the supplementary information for the paper specifically for Juneau, and in the Andy's paper, there's information in the supplement and in the geochronological database as well.
Thanks.
But I mean, I would say watch the space, because we also took some Cosmo samples from moraines in both Peru and in Juneau. And so we may revise our timing of the Little Ice Age or late Holocene near-glaciation once we have those ages.
Well, if nobody else has I have a quick follow-up to that. I'm working with some dendrochronologists that have really never looked at glacial records. They've more looked at precipitation and climate records in Northern California. So what do you have any suggestions for sort of a good paper with how we have a 700-year dendrochronology record and Little Ice Age moraines within that are probably 150 to 300. How would we pick out in the dendrochronology the Little Ice Age peak?
Yeah, I think in Juneau, because the trees are fairly young, they're looking at the age of the tree on the moraine. So the dendrochronology from Juneau is just counting the rings from the age of the moraine on the age of the tree on the moraine. I think if you're looking at things a bit older, I mean, there's various things you can do. You can look at age of death of the tree, if any of the trees have been moved by the glacier and shunted. But I actually wrote a book chapter in Elsevier for cryospheric geomorphology, which reviews that, which you might find helpful.
Yeah.
If you can't find it, just drop me a line and I'll send it to you. But it's a kind of a summary of some of the ways in which we can use dendrochronology to reconstruct timing of moraines.
Great, thanks.
But Juneau, it was quite interesting. We could observe an ecological change across the moraines. With the younger moraines had a different tree species to the older moraines. And we used that to justify the need for cosmodating on these moraines.
Let's see. Philip, did you have a question?
Yeah, I tried to raise my hand, but I don't know which button. Very interesting talk. I'm curious, you also estimate the glacier volume. So what kind of technology you use? You use simple scaling or using some modeling approach?
To do what, sorry?
For the glacial volume work. So what kind of technology you use to estimate the volume of glaciers?
So the volume change is observed volume change. So we use the the satellite imagery itself. So I can go in here. So these are the orthomosaics of 1979 and 1948. And these are stitched together aerial photographs, but because there's an overlap between the aerial photographs, we can use an algorithm to do some complicated maths that generates a surface elevation model. So we have the height of the ice surface. It doesn't tend to work very well where things are very flat and white, but it works quite well where there's quite high contrast on the glacier tongues. And so this shows us how much thinning there's been, because we can take the two elevation models and then difference them. And we can check them because really the rocks around the glacier shouldn't change very much. You'd expect in 30 years them not to change very much. But all of the volume changes are observational based, they're not modeled, and they're based on digital elevation models reconstructed from either satellite imagery or from these aerial photographs.
Okay, thank you.
I'm just always impressed by the ingenuity of some of these, you know, chucking drums of aerial photographs out of an aeroplane and then out of the satellite and catching it in an aeroplane. I think it's really clever.
All right, more questions.
Is there a question in the chat? I can see the chat.
I'm happy to ask a question.
Yeah.
Yes, Johnny, go ahead.
Well, I have not thought about it too much. I'm just curious if the amount of ice loss is enough to show up in the hydrology of the region, whether there's any gauging stations where you can see an increase. And
In Juneau?
Yeah, around Juneau in discharge.
Yeah, there's another team, another independent project, and they have observed an increase in stream flow from Juneau Icefield. I can't remember the reference off the top of my head, but there is, yeah, it's been observed. I think the stream gauge was on the eastern side of the icefield, if I remember correctly, and they've observed an increase in stream flow, for sure.
Is it precise enough that you could check your volume loss estimates using that increase?
Yeah, they generated independent volume loss estimates, and they were of a very similar order of magnitude, but they're using very different methods, and they weren't capturing the runoff from the whole ice field. But certainly their volume change estimates from stream flow were in agreement with our volume change estimates from satellite imagery.
Cool, thank you.
They were a shorter record for the stream flow, but it does capture the scale of the volume loss. We're actually very motivated by stream flow changes, because in Peru and Bolivia and some parts of Chile, the water provided by the glaciers is very important for downstream communities. So we're very concerned that as the glaciers shrink, there'll be less water available for the people who depend on that water for domestic consumption or irrigation or industry. And in some of those basins, we've passed peak water, and the water stream flow is now decreasing because the glaciers have become so small. That's not the point in Juneau. The water is still increasing, but will eventually decrease as the glaciers dwindle away in the future.
All right. Any additional questions? I'll just ask a quick one. The glacier fragmentation, that's a phenomenon that we've been seeing farther south for smaller glaciers in the northern US. And it does seem to have an impact on mass balance, but it's one that I've often been curious about after the fragmentation takes place. So have you witnessed any kind of changes post-fragmentation that could be explained by something as simple as just a shift in ice flow or, something having to do with equilibrium lines?
Yeah, so this map here shows where we've mapped disconnections of fragmentations. So the pink circles here are where the glaciers have separated along their flow line. I have a PhD student called Gunzen Silwal, and she's working in the Himalaya, looking at this process on Himalayan glaciers, and she also sees the same process. So the glaciers are fragmenting over steep topographic bedrock steps because that's where the ice falls are, and that's where the ice is thin. And then it's a similar process of the snow line rising and intersecting with this thin ice. She's also talked about glaciers fragmenting laterally, so that's where they perhaps separate into smaller ice bodies. I didn't map that for Juno. She's taken the research a step further and carried on the process. And that's where they've separated not a long flow, but kind of into separate ice bodies that flow down. All of these are really important for mass balance. And when you have a long flow disconnection, that glacier tongue becomes separated from any ice flow going into it. So it's almost has almost no inflow of ice. And we see a statistically significant acceleration and thinning on Juno ice field for these glacier tongues that are completely disconnected from their accumulation areas above. So that would act to likely accelerate the flow, accelerate melt and ice loss simply because of the lack of inflow. But I think there are also other important processes. So I think the increasing darkness of the environment is important for the albedo. And the rocks that are now exposed are dark, they absorb solar radiation, and we get more radiative forcing that accelerates melt. So everywhere where we see a disconnection, the glacier is shrinking rapidly around it because the rocks are warm. We know this because when we go to glaciers, we sit on the rocks to eat our lunch rather than on the ice. The rocks are nice and warm, but that's not so good for the ice field. And what Gunzen's been doing in the Himalayas, she's been instrumenting some of these rocks to measure the radiative forcing, and she can see how they are directly influencing mass balance. It's not good for the ice field to darken. It's not healthy for the glaciers.
No, of course not. Yeah, and I've been curious about if this fragmentation is accompanied by less snow, or at least less summer snow in the surrounding steep watersheds. What impact that has on the long wave radiation flux in particular. That seems to be something that could really keep that acceleration of loss going. So
yeah, it's a mass loss accelerating feedback that ideally we would include in our models, but you would need a much more complicated energy balance model at a much bigger scale. So it's very difficult to implement on big. If you want to model a lot of glaciers, that's very difficult to do.
All right. Okay. Any last questions for Dr. Davies?
Just one quick comment. Beth, you mentioned about the decreasing of water flow eventually and all that. That's all, I guess that's already, and you probably know this. I guess it's already happening in the Himalayas where the farmers are now building all those ice stupas to give them water during the summer when there's no runoff in the local streams.
Yeah, and in some parts of the Himalaya, there's a really interesting cultural practice of glacier grafting. So in speaking to some Bangladeshi researchers and a team of artists, and they were very interested in glacier grafting, where they take ice from the bottom of the glacier and carry it back up to the top and feed the glacier to try and sustain the glacier. So I think there's a lot of very important cultural significance attracted to this, and local communities certainly know the importance of these glaciers to their livelihoods. They're very aware of it.
In Switzerland, on the Morteratsch Glacier, it's melting so fast, and of course it's a big cultural deal for them. They're trying to figure out a way to take meltwater from an upper lake and string lines across the glacier
Yeah,
to increase the snowfall on the glacier.
yeah.
Try to keep the tourists from coming up the path.
Yeah, I did some field work in Austria last summer, and we visited some of the glaciers in Austria, and it's all a bit desperate. They've been putting tarpaulins on a lot of the glaciers. A lot of them are in ski areas, and so the glaciers are important for their economy. They're important for the tourist economy, for the GDP, for the ski season. And it looks so desperate to see these tarpaulins on the glaciers, and the glacier is kind of retreated around it, and there's this big pile of ice with a tarpaulin on it. So yeah, it all seems very, very desperate. And the problem with all of these geoengineering solutions is they're very difficult to do on a big scale. So you can maybe choose one small glacier to focus on, but that doesn't help on a much bigger, more regional scale. The only thing that's effective is reducing our carbon footprint, unfortunately.
All right. Excellent. Well, thank you again, Dr. Davies, for that excellent talk and for
Thank you for the invite.
kicking off our winter speaker series. I hope you can join us for some of our future talks, or at least view them on YouTube if you don't feel like staying up too late in the evening. And for the working group, we will have our second week of talks next Thursday. That's something that I'll get advertised in an email here. And those will go back to afternoons US time. So we'll share all that. We have lots more to look forward to as our series continues. And thanks everyone for being here today. I'll get the recording posted on YouTube later this afternoon.
Thank you very much.
Thanks again.
Thank you.
Thank you. Thank you.